Comment ça va? Mais oui. Okay. Très bien. Très bien. So my name is James Weaver. Actually, my wife is in the audience, and she doesn't speak much French. So for her benefit, I'm going to do this presentation in English, if that's okay. Okay. Okay, great. Julie, will you please stand up? Actually, so we have been married, we've been married 40 years this November. Thank you. And also I have two co-presenters that aren't on stage with me, but they created this presentation with me, but they couldn't be here. They're based in the United States, and I am presenting, but I'm going to be showing you some video of some things that they've prepared for you, and so they'll be talking to you through video. And so when they're done talking, and each time they're done, if you would give them some applause, I will take that back to them and let them know how good they did or how bad they did. So one is named Mark Heckler, and he is a colleague at Oracle, and the other one name is Sean Phillips, and he works in the orbital science industry supporting aerospace engineering. So my name is James Weaver. If you want to email me, I'm at james.weaver@oracle.com. Some people call me Jim, but do not email me at jim.weaver@oracle.com, because there is a jim.weaver@oracle.com, but for some reason he doesn't forward my emails. So it goes to the bit bucket, so dev/null. So please, james.weaver@oracle.com. Also, I'm on Twitter at JavaFXpert, and I am a developer evangelist. So what we're going to talk to you today about is this idea of these baby steps that we're making, that myself and those other two gentlemen are making in trying to make this AR.Drone autonomous by putting a Raspberry Pi, strapping it to the drone, and then programming it in Java, and making that Raspberry Pi be the brains behind the drone. So I hear music. Is that my music? Am I still playing? I'm sorry, that was distracting. So then I'm going to talk about the anatomy of a quadcopter. What is a quadcopter? How does it fly? And then we're going to tie that in with Internet of Things concepts and tools. And then I'm going to show you a 3D flight simulation that Sean Phillips, one of the guys on the project, made to help us with the idea of being able to simulate the flights so that we didn't always have to keep recharging the batteries in the drone and that kind of thing. So I'll tell you about that, and then I'll tell you about next steps in this project. So first of all, we had to choose a drone, and we also had to choose a foundational library. What API are we going to use to control the drone? And then we also had to decide what level of autonomy that we wanted to have for our drone. And we chose a very simple level of autonomy. We could, in the future, we plan to get more sophisticated, but we have a very simple level of autonomy. So our equipment list is a drone and the brain, which is that Raspberry Pi, and some power. We needed to be able to power the Raspberry Pi, and then trying to make it work, and that's where the story really gets interesting. So which drone? We wanted the drone to have a published API so that people could get support for it. We wanted one that had a nice community and one that was affordable. So we chose the Parrot AR.Drone 2.0. And which library should we choose? So we wanted one that was going to be capable and reliable and responsible. So we decided on one called the Parroteer the Parrots on Java library by Parroteer. And you can see that at parrotsonjava.com. So that's the foundational library that we chose, and then we wrote software on top of that for the autonomous parts. So here's a message from Mark Heckler, one of the...
Hi, I'm Mark Heckler. I'm a software engineer at Oracle Corporation, and I've been working with Jim Weaver and Sean Phillips to bring some intelligence to drones. Oh, wait a minute. Wow,
Yeah.
They're seated awfully close to the front.
Yeah, they are.
Have you all signed waivers?
You signed waivers, right? To
Okay,
security
well, that's great
waivers.
then. Let's carry on. Okay. Anyway, we wanted to provide some intelligence or add some intelligence to drones. What we settled on as a platform is the Parrot AR.Drone 2.0, and that is a really nice, well-rounded drone, very capable, that you typically control with a cell phone or a tablet. And the way that typically works is you control all of the logic, the control on your device, and you connect to the AR drone via an onboard wireless access point that the drone has. So just like your router at home, you're connecting to it as a client. Once we chose the platform, we needed to choose the brain behind the operation, and that's where the Raspberry Pi comes in. The Raspberry Pi is a very inexpensive, very capable computer that, and very small and light, with low power consumption requirements, that allows you to load Linux on it and make several modifications and do several things that would be very difficult to do on another platform. So we loaded Raspbian, hard float, and JDK8 for ARM, and then we set about to make the hardware work. And the first thing you'll probably notice is that we have two Wi-Fi plugs here. What that allows us to do is tie one to an interface which acts as a client to the drone, just like your cell phone or your tablet would, and then to run host APD and an access point on the Pi so that we can connect to it from our laptop and control, take control if need be, but also to push software to the drone or to the brain and to debug it and profile it live and on board, which is extremely nice and very, very efficient. Now that gets the brain on the drone, but there's no way to power the brain from the drone. So what we had to do at that point was figure out a way to provide power to the brain. And that is where this comes in. This is your standard USB charger for cell phones, for mobile phones. And this one in particular provides 2600 milliamp hours, so it's got a good time range. And it puts out 1 amp of current, which if you're using Wi-Fi plugs that don't draw a lot of current, as these Edimaxes don't, then you can run your Pi and the two plugs and everything you need off of this. So what we do to make the magic happen is we use Velcro, and we stick these two together, and then all I've done here is take a short USB cable and plug it in to the Pi and to the power source, and then we turn it on. And as you can see, that boots the brain. So at that point, to make the whole thing come together, all we really have to do is connect the brain to the drone. And now we have the makings of an intelligent drone. So at this point, the drone has a lot more capabilities than your standard. Oh my goodness. Well, I hate it when they become self-aware. Anyway, back to you, Jim.
Well, thank you,
I
Mark.
hope you all have a great session. And again, to those of you in the front, good luck.
Yeah. So Mark talked about assembling the pieces. I won't go through all that, but here's the equipment list: the Parrot AR.Drone 2.0, the brain, which Raspberry Pi Model B, a couple of Edimax Wi-Fi dongles, USB, and an SD card. We powered it with that charger, and then we needed a USB to micro USB cable and some duct tape or Velcro. And so that brain is the central piece of the puzzle, and he explained that a little bit. There's the power supply, which is basically just a lipstick charger, and there's a bill of materials. This presentation will be on the Devox France site, and so you'll be able to then go through that bill of materials if you'd like. And so here's some information that you can go through if you actually try this to set up those access points. Also, there's a website that has the repository for this project that I'll have in the last slide, but it's autonomous4j.org. And so achieving autonomous flight, making it work, we didn't anticipate many issues, but in hindsight, that was just silly. So we did a lot of face palms for sure. We had firmware challenges, API challenges, equipment challenges, and lots of things went wrong. So we expected to be like R2-D2 and 3CPO and Rosie the Robot, and what we got was a bad robot that cuts you, basically, because the spinning quadcopter blades can really hurt sometime, and the thing goes out of control, which is why I'm glad that you all signed waivers so that we don't assume any liability. And a bit of this thrown in for good measure. A lot of the testing was done at Mark Heckler's house, and he actually had to move out of his house because he ruined too many drapes and too much furniture, and his wife kicked him out. So this is the drone flying with the Raspberry Pi on top of it, and it kind of demonstrates why I'm not going to actually show you the Raspberry Pi flying, because it's kind of unstable. So I wanted to show you in a video. Notice he's got a filament wire there that keeps it from wrecking his wife's drapes and flying down the stairs. But notice how unstable it is because of that extra weight on top. So anyway, what I'm going to show you then is without the Raspberry Pi. Instead of putting the software on the Raspberry Pi for this demo, the software is actually running on my computer, on my laptop. It's the same idea, but just without that extra weight that might make this thing spin out of control and hurt somebody in the audience. So the anatomy of the quadcopter, here's a quadcopter, and there's, of course, a picture of it. You have 4 spinning blades of doom, and they have brushless motors, and each one has its own motor controller. And then we have a lithium polymer battery, a 1 amp battery. And then we have an onboard wireless access point, and then an indoor shell. This is the indoor shell, the styrofoam. And on board it has an inertial measurement unit. That's an IMU. And that has a gyroscope with 3 degrees of freedom. So it can measure roll, pitch, and yaw in nautical terms. It's got an accelerometer with 3 degrees of freedom, so it can sense acceleration in 3 axes. And then it's got a magnetometer, so it can tell where it is relative to north. It's got an ultrasound height sensor, so as it's going over the floor, then it's shooting sound waves down and then measuring how long the sound waves take to get back to measure its height. It's also got a pressure sensor so that as it's flying higher, it can know how high it is based upon barometric pressure. And it's got a front camera at 700p, and then a downward camera, and that downward camera can be used to show images, to beam images back, but also Another thing that it's used for is for odometry, so that it can, as it's moving along the ground, it can sense how far it's going and how fast it's going. So that's one of the additional features for being able to kind of tell where it is. And the flying principle is the only control that it has is the 4 quadcopters. So if we want to make it do this, then we just spin these blades faster than these blades. We want to do this, these blades faster than these. Same thing this way. If we want to do in the yaw direction, we want to change the yaw, then we spin these 2 blades perhaps faster than these 2, and that way there's more torque in one direction than the other. And so that's how that's the flying principle of the quadcopter. So I'm going to go ahead and demonstrate, and remember that there are a lot of pieces to this demo. So please forgive me if it doesn't work or if it spins out of control. Don't try to like catch the drone if it comes out there. Just kind of nudge it or something. Definitely don't grab the blades. So this was written in a library. We created a library on top of the foundational library that has an API that makes an instance of the brain, and then we can give it commands like take off and then hold for X number of seconds. I think that we're going to hold for, actually, let me just show you the real code. Programmers like real code anyway, right? So I don't know whether you can see this. Do demo box flight. Can you see that? Yeah, you can see it. Okay, so what we're going to do is we're going to make it take off from this point here. It should hold for about 8 seconds, and then it's going to go left, you're right, at 20% of speed for about 5.5 seconds. And then we're going to have it hover over there for 3 seconds, and then it's going to go right, its right, your left, at 20% speed, hover for about 2.5 seconds, or do that for 2.5 seconds, hover for about 3 seconds, and then land. Okay, so let's give that a try. That should be fun to watch. It's never worked before, but maybe it'll work for the first time here. I don't know. Let's try. See? So actually I did. So now it's got a mind of its own, I guess. Okay, there's its 8 seconds. Now it's flying over there for however many seconds. And then, now come back to me, come back to me. Now hold there, now land. There we go. Perfect. Good job, drone, good job. I'll give it a fish or something a little later, some kind of treat. Okay, so that was that. Now, here's some other things. I don't want to press my luck with too many demos, so I'm going to show you some video demos of some other things that we built into this autonomous software. For example, we have this go home functionality. So we want it to be able to do different things like take off, forward, hover, go right, go back, whatever, and then go home. And then it would calculate, based upon the commands we've given it, to go home. So I'm going to show you a video of that particular thing, where Mark did that in his living room. So now it's going to go backwards, or right, left, whatever. Kind of make a pattern, and then we're telling it to go home. Okay, so it almost made it home, right? It wasn't exactly perfect, because there could have been things like wind and other variables, and we'll address those, and that's some of the things that we're going to do to make the software smarter in the future. So then here's an example of controlling LEDs. One of the things in the foundational library that's supported by the AR.Drone and then supported by this foundational library that we're using from Parrots on Java is this idea of blinking the LEDs and with different colors. And so here's a video of it taking off and holding for 6 seconds, blinking green, holding, blinking green, holding, and landing. So just showing you the idea that we can blink the LEDs. Okay. And then now what I'd like to do is kind of get into some IoT tools and concepts. Internet of Things is this idea. I'm sure you're all familiar with the Internet of Things, but it's this idea where you have all these things, devices, wearables, sensors, actuators, things like that, everywhere that are connected and able to then talk to each other and work together cooperatively to do something. In this case, we're going to demonstrate some concepts from the Internet of Things. We're going to demonstrate a tool and a protocol called MQTT. And that's just one of the protocols that's commonly used in the Internet of Things. And there's a software package called Mosquito. It's an open source MQTT package. That's an MQTT is this publish and subscribe kind of thing where a device can publish on a port, and then you can subscribe and then find out what events are happening in the device. Also, we're using NetBeans. We're of course using Java. And we're using this MQTT control browser and controller written by Jens Dieters in Germany with JavaFX. So here's the idea. We have the drone that's got a Raspberry Pi for brains running Java, and it is running this Mosquito process, publishing to a particular address. And then here in this MQTT software, we're going to subscribe to that particular service. And then we're going to display, we're going to tell it, first of all, we're interested in certain messages, and then we're going to go ahead and display those messages. So here's the demo. And then we'll get to that here. So here's MQTT, and then we're going to start up Mosquito. Now Mosquito would normally then be running on the Pi, as I just showed, but we're go ahead and start up Mosquito, and then we're going to go ahead and connect to that service, and then I'm going to subscribe to our messages that we've created, A4J nav data. So the navigation data that happens on the drone, we're subscribing to so that we can then display that over here. So nav data will be things like pitch, yaw, roll, angles, and acceleration on XYZ axes and other kinds of data. So did I subscribe yet? I'll go ahead and subscribe. And then now we will press our luck one more time and run that. And we should see, where's MQTT? So now we see the MQTT messages fly by as the drone makes its flight. Hey, you didn't go far enough. Go over there. Go farther. You're being a bad drone. Hey, no fish for you. Okay, so anyway, the point is that, oh, well, thank you. I don't think the drone deserved your applause, but you're very kind. Thank you so much. So then here's the navigation data that we got. So we got approximately in that amount of time we got about 1,300 records of navigation data. Like for example, what the battery levels are, the pitch, the roll, the yaw, the speed on the X and Y axes. I think that's about all the information, and so it was giving us those, 100 times a second or something. So that's the idea of using some Internet of Things concepts in this domain when we're flying drones autonomously. And so now I'd like to discuss this idea of being able to provide a simulation of the flight so that we don't always have to charge the batteries in the drone and take it on lots of test flights and ruin our drapes and furniture. And so we asked Sean Phillips, who works in the space industry, to create a 3D simulation. And so here's a message from Sean.
My name is Sean Phillips, and I work for a company named AI Solutions. We provide access to space for both NASA, the U.S. Air Force, and other space agencies around the world. We're located just outside Washington, D.C. I was invited by Mark Heckler and Jim Weaver to help them with their Java 1 session this year titled Welcoming Our Robotic Overlords. Their bright idea was to take a bunch of 4 quadcopter drones and attach Raspberry Pis to them and then give them all the smarts that they need to go flying around the audiences without chopping people's heads off. And so far, nothing bad has happened. So in the meantime, they said, well, we're having a lot of trouble. It's a lot of work to try to test the code and try to get these drones to move around. It'd be really nice if we had a 3D simulation that could help us test some of this stuff. So instead of Mark Heckler flying his drone around in his living room in his house and breaking his lamps, he could instead fly it around on the screen and just break pixels. So they asked me for some help. So I decided to use JavaFX 3D. So I used a few libraries to do that, and Jim Weaver is going to demonstrate some of the software I made that live and show you some slides to go with it. I won't steal his thunder, but I would like to mention a few technical items. First, I use a great model loading library called from Interactive Mesh. It loads 3ds, Collada, OBJ, etc. For this project, I have several OBJ assets in with the source project, a TIE fighter and an X-Wing fighter. You'll see that in a moment. For the 3D cube world that you see, I had that from FXYZ, which is a third-party, open-source JavaFX 3D component library, providing anything from 3D scatter plots to skyboxes to all kinds of shapes and billboards. And finally, it should be noted that the method for navigation I used is a simple form of dead reckoning. Dead reckoning is essentially taking the taking the commands and the data that you receive from your real-life system, i.e. the drone, and performing estimations and tracking those estimations. Now there's a problem with that, of course, and that is that if the estimations, in this case in the 3D world, don't match the actual world movements of the drone, there gets to be a cumulative error. That is an error that's adding up over time that you, as a dead reckoning system, can't determine. So that's one of the weaknesses of this current code, is it's dead reckoning around in the 3D world. So if you look to extend this example that we're providing with this presentation, please keep that in mind. The other thing to keep in mind is that we designed this code to be very flexible. The code was written in such a way that new commands could be built, defined, parsed with whatever rules that you would like to have. And so you'll see that it's very easy. I used NetBeans 8 to do that. Yeah, there it is. And you'll see that there are 3 really major classes you need to address. The autonomous 4J3D sets up the 3D scene, adds some mouse and keyboard handlers here, and accepts commands via drag and drop, as Jim is going to show, and then recognizes those commands and then issues commands to the drone. That's handled in the overlord class. The overlord defines your drone, and this is where you tell it to say, okay, if you receive this command, this is what you need to do on the screen. And you'll see that I've relied very heavily on transitions and translations, as you would expect in a 3D scene, but I also rely heavily on timelines and properties. And the reason for this is I couldn't use standard paths because the standard path in JavaFX is only 2D. It does not support 3D translations. So we kind of had to hand tool it a little bit. Finally, if you want to change how your drone moves, or if you have a different type of drone, you're going to need to play around with the formulas that perform the dead reckoning itself. And that is here, the sensitivity variable, and also the power, and to a certain extent, your duration calculations. All right, well, thank you for your time. I hope you enjoyed the demonstration, and back to you, Jim.
Hey, thank you, Sean. So Sean went through these, the 3D modeling and some of the techniques and the specifics of the classes that he used, and they're in open source, and you'll be able to see those at the, if you go to autonomousforj.org. And so I'm going to go ahead and demonstrate using a flight file. We defined a file called AFR, Autonomous Flight Recording, and then here's Sean's simulator. I'll go ahead and start that up. I don't think I've already started it up. Maybe I have. Yes, I did. Okay, so then we'll take this flight data. And this was one that actually flew in a box pattern. So I'll go ahead and drag it here. And then the drone is represented by a TIE fighter. And so then it's showing the commands and the effects of those commands in 3D space. So that way we could see the flying characteristics of the drone without having to fly it all the time. And there it is landing. So then the next step that we want to take is to add to the autonomy, give it a more advanced level of autonomy. So some of the next steps would be to create an external control loop, and so that it could do self-adjustments then to be able to achieve a particular goal, and then give it higher level goals and commands. And we might actually have to change the platform to make that happen. So here are some of the things that we're considering. First of all, with the AR.Drone comes a piece of paper, a cardboard cutout that's about an A4 size piece of paper that has, it's called an oriented roundel. And you'll notice that it's black and white, and if you are looking at that through a camera, you can tell where you are in position, in relationship to that roundel in terms of yaw. Okay? But also, we want to be able to tell where we are in XYZ space. So, the first step to be able to provide a control loop where we can say, instead of flying 3 seconds at 20% power and land, go somewhere over there and fly 2 seconds at 20% power and come over here, as we've just talked about, that's not very reliable because you could have wind and other variables. So what we want to be able to do is say, go to a particular XYZ coordinate, and then hover, and then come over to another particular XYZ coordinate. So, and then we would let the underlying autonomous libraries that we create figure out the speed and directions and things like that that it's going to take to get there. So that requires a control loop. And a control loop is something that's very common in control theory, and it consists of the following loop. So we have a desired pose. The pose is the position of the drone. Where do we want it to be? Maybe we want it to be over there at right beside that Devox France banner. And we want it to be oriented at a 45-degree angle in the yaw direction. And so we want to be able to tell it that and have it go there. So that's the desired pose. So the measured error is measuring where I am right now. And so how do I measure where I am right now? Well, I can use this oriented roundel. Not only can I tell my yaw because of what I just said, but I can also tell my XYZ position because in the bottom-facing camera, I know what pixels that I see that tag, that are around that tag. So the AR.Drone reports, as it's reporting the flight data, it also reports that it sees that tag, and then it reports what pixels outline that tag, the 4 pixels that define the rectangle that outline that tag. And then using some linear algebra and some matrix transforms and some pre-calculus kinds of ideas, you can then determine where you are in space. So then you've determined where you are based upon what you've measured. You have your desired location, and then you have to apply some control. Now remember, the quadcopter just has 4 blades. Those are your control. So your controller then is going to do the calculations for how fast should I fly and in what direction. So that control loop is a little bit like when you're taking a shower in the morning, for example. You turn the water on, and you want it to be a nice temperature, and so you stick your hand, you don't just jump right into the shower, right? You stick your hand in, and maybe it's a little cold, right? So then you turn it up. Well, how do you know how much to turn it up? Well, you try a certain thing, and that's called gain. In the control theory, that's called gain. And so I'm going to turn it up a little bit, I'm going to check, and I maybe turn it up a little more, check, and maybe it's too hot now, and so maybe I turn it down. And so that's this idea of this control loop and applying gain. And so the amount of gain that I apply is, you can apply different algorithms to it. So one such algorithm is called a PID controller. That stands for proportional, integrative, derivative kind of control, to where the proportional part is what I'll talk about right now. But the proportional part is where maybe in the shower it was very cold. And so if it's very cold, I'm going to turn it up farther than if it was almost the right temperature. So I'm making a proportional adjustment, a proportional gain. So in terms of rotor speeds, if the measured error is pretty far away, then I might compensate with that. I might apply a control that makes the rotor speeds make the drone go faster toward that destination. And then at very frequent intervals then, we would use the sensors to measure the position. So what sensors are we using? Well, we're using the sensors in the IMU, which were gyroscope, magnetometer, and accelerometers in all 3 directions. But then we're also using the oriented roundel to figure out where we are. So between all of those, we are measuring the pose, and here we come back to measured error. Are we where we want to be? And if we're not, then we apply that again. And then we arrive at the place that we want to go. And then maybe the next place, then we say, okay, now that you're there, I want you to go here or do this thing. So the difference is between what we have which is code that you saw, which are things like go right at 20% power for 1 second, where we give it percent of speed and duration, we could say things like the desired pose equals this new pose object, which is 3.5 meters in the x-axis, 4.8 meters in the y-axis, and 0.3 meters high. And the yaw, we want you to be at 45%, and now move there. Okay, so that's the idea behind that. So in conclusion, first of all, thanks for attending, but also please tweet myself or Mark or Sean, and do visit autonomousforj.org if you'd like to actually get your hands on the library and take a look at it. And I'd love to entertain any questions that you have.
I'm just curious why you wanted to attach the Raspberry Pi on top of the AR.Drone instead of just keeping it on the ground, because it adds some weight and can communicate via Wi-Fi anyway.
Right, so put it underneath.
No, just keep it on the ground like your remote controller, because it's Wi-Fi connected.
Sure, because we wanted to be cool like that. We wanted to be cool to where it's kind of on board, right? So we've got this unit. Now, in retrospect, that's one of the facepalm things, where it's adding too much weight up here. Well, why not make the drone legs a little bigger and put it on the bottom? So we may do that next time. But yes, very good point. Thank you. Merci. Let's make sure Stefan gets his exercise here. So people in the back row have to ask questions so that Stefan can get his aerobics in.
Why don't you use a kind of sat-nav to position the drone?
Why don't I?
Sat-nav.
GPS
yeah,
signals,
GPS.
yes. Okay, if we are, the question is, why don't we use, well, everybody heard the question. Okay, so why don't we use like GPS satellite navigation, right? So first of all, we're indoors, and so I can't. But second of all, but if we were outdoors, if I were building this for outdoors, that'd be perfect. It'd be a great thing, and that may be something that we do. It'd be great to get some vitamin D, and while we're actually coding. Other questions?
Hello. Your simulation program does take control inputs, commands input, as I can see. Do you plan to make it more usual with the Java program you make? So
okay.
You use exactly the same code that you push in your drone in the simulator?
Okay, so the question is, the 3D simulation seems to be like different. It was done in Java 3D, and it seems to be different than the software that we're putting in the Raspberry Pi on the drone, right? So do I plan to make that exactly the same code? And so the next step, that's a very good question. The next step where I'd like to go with this is I'd like to notice that that we're dragging and dropping that recorded flight into the 3D. So what I'd like for the next step to be is for it to be communicate interactively, maybe with MQTT, right? Where as the drone is flying, it's publishing its nav data, and then the 3D simulation is subscribing to that nav data, and so it knows precisely where where it's trying to go, right? And since it's reading the tags, it would know precisely where it is. So there's two modes we could go in. One is to show precisely where it is, but then the other mode would be to show the controls and then show probabilities on where it is. So if we said go 20% power for 1 second, then the probability is that it would be somewhere in this circle. But we don't know exactly where unless we get a reading from the, unless we can see the tag. So we would show in the 3D simulation a circle or a sphere saying, this is probably where it is. And then when it does get a reading from the tag, then we can show exactly where it is. So being very interactive that way, not the same code, but working interactively at the same time, which is, I think, was probably the reason for your question. Yes. Thank you very much for your question.
So I got a question for the audience. Parrot, I believe, is a French company. So are there any Parrot engineers in the room? Okay, too bad.
Yeah, they were, Parrots on Java was extremely helpful in this. They were helpful in providing that library. We had seen them at other conferences, and we immediately asked them, hey, can we use this? Because there were other couple of APIs underneath it, but they weren't nearly as reliable. And the Parrots on Java people, yeah, the French company was awesome. Awesome.
Any more questions? No?
All right, guys. Thank you very much.